Okay, let's kind of shift gears here. For lecture 3 and 4, we're going to talk about network models, and specifically we're going to talk about transportation model as an example. So you'll be able to sort of recognize this. It's one of the more straightforward kind of economic diagrams we have. Really, the issue here, and as you read through the book chapter, I'm going to go through this kind of fast because the reading, I think, does a nice job in this case, and we're doing the exact same problem as in the reading. But the real issue here isn't so much about what kind of choices do I make, but it's this problem you can see here as I build this up, and I have this diagram with sources on one side, destinations on the other side, and I know that I want to, as cheaply as possible, move things from this side of the problem. It's a transformation problem in that a good at location A has a different valuation than a good at location B, and the difference in those values is the cost of moving them there. Okay, and so we call that sort of a location utility if we were thinking about demand. But the idea is that the demand at these different places is sort of maybe set by the ability to sell things there. In this problem, not so much. The only thing in the problem we're going to do is you have to get the things here because that's where they're needed for the next step in the process. So it's sort of this node in the production plan where we get some outsourced or whatever off of one plant produces something, and then to get to the next plant where things are going to be assembled, we have to do some movement. Okay, so we have to transport these things. Each of these nodes or each of these branches going through here has a cost. That cost is probably somewhat proportional to the distance to be traveled. It could also relate perhaps to quality of the roads, the type of roads, the type of transport units that are available to move things. However you want to think about it, but we're not going to worry too much about where all these costs come from. Well, what's interesting here is just how big this problem gets. Okay, so you start out with, I've got things at one source and maybe 4 destinations. Well, you've got 4 choices. You add a second source, you just added 4 different choices. And so now you're trying to compare, when I ship something to destination 1, should it be from such source 1 or source 2? Then when you add down to destination 2, what happens if you also want things there from source 1? And destination 3, you also want those to come from source 1. Well, where does the first unit out of source 1, right, this low-cost source, where does it go? How do you fill this out? And it's a big dimension problem, and the real trick to these isn't sort of in mastering the economics or mastering the idea, sort of the economic theory part. It's really about how do you manage this dimension, get it into a spreadsheet, and get linear programming to solve it for you. And so that's where we're going to focus. So let's take our example problem here. Again, this is assigned reading, so I'm going to go kind of quickly through it. We have assembly plants. These are the destinations. That's where they have sort of a demand side or a requirement. These numbers are required, and so we have to get at least 400 units, at least 900 to these 4 assembly plants, 1, 2, 3, 4. The sources, or the supply side, is these 3 cities, A, B, and C, and the number of motors that are available to be shipped. Now, I think I mentioned already in a previous lecture, there's this overriding constraint, this sort of total. If you have to get at least 400, at least 900, at least 200, at least 500, that means there's a total amount. You have to have at least 2,000 in total. And so here, this number down here, when you add all these up, has to be at least 2,000. Otherwise, you're going to come up short and have an infeasible problem. And so we always sort of check that at the start, and this one turns out to be perfectly balanced. And if you read the reading on transport this week from, I think it's Moore and Weatherford book, in this module, you'll see they talk about some of the implications of a balance problem, and we'll talk about those in our lecture following this one. So the sources are labeled. If you plotted them out, you would see that there's these differences on the map, and this is the same graph I showed in lecture 1 of this module. There's some plotting that goes here that sort of gives you the feeling of what the different costs might be. So it's not just that picture there where we're drawing straight lines through, but you would need some information on the economics of moving something from this place, Le Havre or C, to Tilburg versus Liège versus Leipzig. So you need to know those things. So how do you compare those routes? Well, you need some cost data. And we do not talk about where do you go find that cost data. I've already talked a little bit about how the information may be there, but for any firm that's out there moving things around, they will have tracking on this. They'll know what they're sort of spending. Every time they ship something on that route, they'll be able to put it on a per unit basis, and that's what we have here, sort of a from origin to destination, or a source to sink, source to destination per unit measure, and we do it in this matrix form. So we say matrix because we have rows and columns, or tabular form if you prefer. The intersection of a row and a column tells you the cost of shipping something, a 1 unit shipment from Amsterdam to Leipzig increases our cost by 120. 1 unit from Amsterdam to Liège increases our total cost by 41. Okay, so we have this cost matrix that gives us all the per unit costs. And if you move across the row, you're comparing, sort of how good or what are the costs associated with Amsterdam, the costs associated with Antwerp. Moving down a column, you get what are the costs associated with Nancy versus Liège. And you could do some comparisons. You could do a very typical thing to do would be for someone, a statistician, to look at this and say, well, I'm going to take the average cost of shipments to Tilburg and compare those to Liège and compare those to Nancy. Then I'm going to say, if we had to decide which assembly plant to shut down, and we wanted to know sort of a measure of the total cost, and which one is sort of costly for us to get these motors at these sources into the assembly plants, we'll figure it out using sort of an average statistical basis. Well, you can see from the matrix that would be kind of a weird thing to do. That would be very short-sighted, because it's possible. Look at this. The smallest number. This is an average, total of 260. Here's a total that's 280. Here's a total that's also 260. Here's a total that's even lower than that. It's maybe I'm having trouble doing that. 200. So this would be like the lowest average cost, but the lowest cost route here is 40. And so shipments from Antwerp to Nancy are very small, very low cost, but to Tilburg, this lowest cost on average place, they're very large. And so we need to be able to model this, figure out not what the average is for all of our costs, but what's the average, or what's the best and worst places, the most and least costly sort of destinations and sources in our solution. And so to do that, we need to solve a linear programming, and then the lecture following this, we'll talk about the sensitivity, and that's really how we'll focus when we get there. Okay, so how do we implement this in a spreadsheet where we're going to keep this sort of matrix design that comes from the cost information table? So an intersecting cell for a source and destination is the per unit contribution to the objective, in this case, the per unit cost. So Antwerp to Leipzig, the cost will be 61. The solution will only be as good as this cost information. That's something to keep in mind. So if we were fudging numbers or sort of putting these in, if we believe the best information was related to the distance, then we could just use the straight distance value and think about per cost miles. But typically, good cost matrices will include more than just an average cost of running one of the transport trucks or whatever that distance, it'll include the specifics of those routes and what kind of roads and what kind of movement you can get on those. So we're going to use, for step one, we're going to use the cost information matrix. That's sort of our parameters, or if you think about it, the objective equation coefficients. The second step is to set up an activity or a choice matrix. Okay, so we're going to call it the use matrix. How are we going to use, so of all the routes we have to us, we have the number of routes here being the sources times the destination, so 3 times 4, we have 12 choices in here. Some will be set to 0 and some will be set, you know, to ship a motor from the source to the destination. So we have to set that up. And so this block of cells in here all start at 0, and these are the things we're going to let Excel choose, right? We're going to set solver to run. It's going to make adjustments in these, and it's going to tell us the best plan by telling us which routes we should be shipping motors on. So initially they're set to zeros, and then the nice thing about this is we can build our constraints because we have this matrix set up where every row is defining a source over here, every column is defining a destination. Then we can set up our constraints right at the end of the choice matrix. So if this row tells you how many units you're going to ship to Leipzig, to Nancy, to Liège, to Tilburg, you add them all up, and so we don't need those sum product formulas now. All we need is a summation. Just add this row, put it in the left hand side here, and then compare it to the limit, the upper bound of 500. That's the most you can ship. Same thing if we go down a column. We have to use the number of shipments to Tilburg from Amsterdam, from Antwerp, from Le Havre. Add all those up and put a sum here in what we're going to call the left hand side value. And we know that that number needs to be larger than or equal to 800. We have to meet that minimum requirement at Tilburg. And so that's the second piece of our matrix setup here that we're going to use. So in this second matrix, the choices and constraints matrix, we're going to get the choices inside this block, and then left hand side, right hand side combinations, or comparisons, going to be built right off of the end of those rows using simple summations. We need one more matrix, and we'll have a full problem set up. Step 3, the cost contribution matrix. So matrix 1 is the cost per unit of a shipment from Amsterdam to Leipzig in this cell. This number going from 0 to 1 will increase the cost by 120. To 2 it'll be 240, 3 will be 360. And so what we can do in that third matrix to get the total cost contribution is multiply this cell in the top matrix by its corresponding cell in the second matrix, the choices and constraints matrix. And then in our third matrix, the cost contributions by route, we will report here the cost per unit times the number of times this route, the cost per unit shipped on this route times the total number of units shipped along this route, and we'll have a cost contribution right here. When we do that, we can add those up and do the source. We can add up everything inside of this matrix. These are all cost contributions in here. Add it all up, calculate that as a sum, and we get the objective variable, the total cost down here in this cell. You can also measure the total cost by destination, right? So this may be interesting information. What is our contribution of cost not on each route but on each destination? How much of the cost, what percentage out of the total cost is going on just meeting the Leipzig versus the Nancy versus Liège and Tilburg constraints? You can do the same thing on the source constraints too, or here. So the source contribution, what's the total cost of shipments out of Amsterdam, and how big is that relative to the other sources, and how big is it as a share of total cost? And then I wrote in a little check cell here. I think it just subtracts this sum from this sum, and it says you better get the same thing when you add up across here to here. It's just one of those places where you can write in a little check on your model and make sure that you haven't, because this is kind of a unique setup where we have to make sure that the match, the product or the multiplication that's being done in this cell matches the correct cell above, and that we're also meeting the constraints. We can check that in that cell. Not an important piece though. So let me I want to pause and I'll reopen, I'll continue this video, sorry, looking at the spreadsheet with you just to walk you through the three matrices and look at the formulas. Okay, you have this spreadsheet in your workbook for this week. It's called Lecture 3 Transport. It's fully set up for you. And you can see the matrix setup. So this thing gets a little big in the spreadsheet, so it's not terribly efficient in terms of using the space, but I've also blown it up here, hoping it'll screen cap better, or screen grab, sorry, capture my screen as I talk about it better if it's a little bigger. So we have our cost contribution matrix. These are hard-coded numbers, right? These are the exact parameters. So if somebody came along and said, hey, we've got a new estimate on shipments from Amsterdam to Liège, it turns out we're paying 10% more because they've added a toll or whatever in there, or there's some road work that's slowing us down, it's increasing that cost. You could come in here and adjust this directly. Okay, so we could change that. That would be where we change these sort of prices. We know that price ratios matter, and so you can see that why the spreadsheet becomes, or computational models become important. You would go a little bit nuts trying to think about all the right ratios you have to do here, because there are 12 things that have to be compared. So this is the sort of hard code information. The other piece of sort of hard code information are these right hand side limits. So if for some reason the capacity or the at one of these sources went up, right, we ended up with a little bit better production than we thought, and we're now getting 550 on average every quarter or whenever these are being produced. Well, that's where you would make those adjustments out here in these right hand side values. That's the hard code stuff. In here, these are just numbers. These are just zeros that Excel is going to change. So this entire block, be careful when you make your selection in Solver for your choice variables. I've seen very many people in labs grab all of these zeros, and you do not want it changing the left hand side. So everything in here, everything that's an intersection between a source and destination, is a choice variable, and Excel needs to have those free to move around and adjust to meet these constraints and to make the cost as low as possible. We said the left hand sides were just going to be sums, and so true enough, there it is. It's the sum of those three cells, and that gives you the left hand side for the Leipzig constraint. Sum those three cells, you get the left hand side to be compared to 900 for the Nancy constraint. So you've got to get at least 900 units there. That sum needs to get to 900 for this problem to be feasible. Okay, same thing over here. We're going to sum over a row in this case. Alright, if we slide down here to the cost contribution, I said this should be the multiplication of this cell times this cell. And so I'm just going to click it, and you'll see, sure enough, it is B9 multiplied by B3. And so it says if this number changes to 15, then 15 times 120 gets me to 1800, and that's the cost contribution of that choice, of making that, planning on that shipment. I guess I could have left that, yeah, so we can see these other formulas work. So you put 15 there, you see that you've added to the left hand side on this constraint, you've added to the left hand side on this constraint. You've pulled 15 units from the source, you've now built up 15 units at the destination, you've added 1800 to total cost, and you've attributed 1800 in the cost on Leipzig, 1800 cost to the Amsterdam as a source. Okay, so it's important to keep in mind when we do these costs out here, we're overlapping, right? So every choice has both a source and destination component, so we can measure it on the left hand side here and the left hand side here. Even though it's only one unit, it shows up that one time, or those 15 units show up in this constraint and this constraint, and those costs would show up in the contribution cost in total for the source and for the destination. But we only want them to show up once down here in the objective. So that's why when you look at the objective cell, we're going to only add up the actual contributions inside the matrix. All right, so those 12 units in there. Obviously you could just add up the columns or the rows as well, but you have to be sure you only do it once, Otherwise, the number is just totally wrong. So this is how I've set it up, and that's how I want it done. And then I did mention this check cell, so you can just see that I'm going to add up this row and subtract it from this column. All right, so take the sum of this column, the sum of this row. That better be 0, in that way, because if something's being shipped, it has to account for some cost here and some costs here. That's the setup. You have this spreadsheet, and we're going to solve it and work through the sensitivity information.